We present BiScale radiance transfer, a technique that precomputes fully general view and light-dependent transport effects at both a coarse and fine scale. All images were recorded in real time from a PC with an ATI Radeon 9700 graphics card. We begin with a demo of BiScale rendering effects. Precomputed radiance transfer, or PRT, stores a transfer matrix per surface point to provide effects like self-shadowing as the lighting or object moves. The technique is impractical, though, for fine-scale effects. Bidirectional texture functions, or BTFs, are suitable for modeling fine-scale effects, but ignore global effects specific to a particular geometry, like shadows from one part of the bunny onto another. We first extend BTFs to use the spherical harmonic basis for lighting. We call the result a radiance transfer texture, or RTT. RTTs allow very large light sources in lighting environments in real time. Finally, we combine these effects in BiScale rendering. This provides correct shadowing and shading effects at both coarse and fine scales. We switch the coarse scale effects on and off to show enhanced realism obtained by simulating geometry-specific transport. Here we show a demo of a radiance transfer texture mapped onto a simple square. RTTs capture both view and light-dependent appearance in terms of low-frequency lighting, recorded over a small patch. Note the change in appearance as we move lights or rotate the patch. We can also change the light source size, simulating appearance of the patch on a cloudy day. Rendering cost is independent of the number or size of light sources. RTTs also change appearance with changing view, including self-occlusion and parallax effects, called masking. Without masking effects, the texture looks much flatter and less convincing. The fine-scale transfer simulation, represented by an RTT, can then be mapped over a 3D object using texture synthesis. We parameterize the 3D model and synthesize an ID map, which records RTT indices as a texture over the model. This map is visualized in texture space by mapping its two outputs to red and green. Here is the ID map visualized over the 3D model. Note the patch-like appearance, where texture synthesis has mapped different parts of the surface from a contiguous group of RTT spatial samples. Finally, here's the rendered result, including both coarse and fine effects. We can map fine-scale texture from a library of previously simulated RTTs onto the same object. Here we map both synthetically generated and acquired RTTs onto a simple vase model. We end with a variety of real-time results of BiScale rendering with various RTTs and in various lighting environments. We turn masking on and off to show how view dependence in the RTT enhances realism. Note the unrealistic glowing effect produced when the coarse scale effects are turned off.